Hi everyone and welcome to another video. So today I will be showing you how to integrate exponential and logarithmic functions. How does this work? Let's find out in today's video. Alright, so today we'll look at how to integrate exponential and logarithmic functions. So if we consider integration as the reverse process of differentiation, then the following illustrate the way in which exponential and logarithmic functions can be integrated. As you can see, you remember from derivatives that when you integrate ex, when you differentiate ex, it actually remains ex. So in the same way, when we integrate the ex, it's also going to be ex, but now we're going to add a plus c to just consider that constant that may be there. Then also when we integrate the constant a to the power x, as you can see there, we get ax over ln a plus c. So that's actually how it works. And then if we to integrate 1 over x, definitely that's going to be ln x, because when we were finding the derivative of ln x, we always stated it as 1 over x, and this is how they're going to be. And obviously we're going to be having to add those constants at the end, especially in cases where they are actually indefinite integrals, and that's going to be the case. Alright, let's look at some examples, and this will actually enable us understand this even better. Alright, so in question number 1, we're being asked to evaluate e to the power negative x dx. So we're being told to integrate that. So how do we do that? Now, in this case, we're going to make use of u-substitution. So u-substitution, as we've learned in the former video, is going to be very useful in this case. So we're going to let the u to be equal to the negative x at the top. So therefore du dx is equal to negative 1, and then dx shall be equal to negative du when you actually make dx the subject. So therefore we have eu times negative du, and then as you can see, we'll have a negative 1 which we can actually pull out of the integral. So we'll have it like this. Now integrating eu alone as it is actually easy, because you know the integral of eu is going to be eu plus c. And then we will not forget that there is a negative sign outside here, so we'll multiply it onto the answer and we'll have a negative eu plus c. But remember that u represents negative x, so therefore our answer is negative e negative x plus c, and that's how we integrate this kind of number. Alright, let's look at another number to understand this even better. How about if you're told to evaluate the integral of e power 4x? What answer do we get when we actually integrate this? So as you can see, we can let u-substitution is going to be very helpful. We're going to let u represent the power 4x, and then du dx is equal to 4, and then if we make dx subject, dx shall be equal to du over 4. So substitute that back in, and we have eu times du over 4, where we have dx, and then we can pull out a quarter from there, and then we know the integral of eu is definitely eu. But remember that u represents 4x, so therefore we have a quarter e power 4x plus c. So that's actually that's the answer of the integral of e power 4x, and that's how we would do such a number. Alright, so moving on to question number 3, we're being told to evaluate the integral of x squared plus e power 1 minus x dx. Now clearly here you can actually see that, first of all, because there's a plus sign in the middle, we can already split this into two separate integrals. One where we integrate the x squared, and the other one where we integrate the e power 1 minus x. So let's deal with the side of the e power 1 minus x, because the other one is obvious. Now in this case, when we have e power 1 minus x, we're going to use u substitution. So we're going to let u be equal to 1 minus x, of which du dx shall be equal to negative 1. If we make dx a subject, it will be equal to negative du, and then therefore this is what we end up having. So these are the two different integrals, but now we've used u substitution on that side where we're integrating the e power 1 minus x. So next you can see we can actually factorize out the negative here, and we should factorize out it as a negative 1, of which it will affect this plus sign, and that's why it becomes a minus. So we have now the integral of x squared dx minus the integral of eu du. Now this is easy, because the integral of x squared shall be equal to a third x cubed minus, now this also remains as eu plus c, and that's what we end up having. But remember that u represents 1 minus x, so we're going to substitute that back in, and then we'll have a third x cubed minus e power 1 minus x plus c, and that's the answer that they wanted. So in question number 4, we're being told to evaluate this, the integral. Now this is actually a definite integral with an upper limit of 1 and a lower limit of 0. So we have 2 to the power x plus 3 to the power x over 7 to the power x. Now this is an example of a constant that actually has a power that is in terms of x, and as we've already seen how this is. So but let's work this out. Let's take it one step at a time. So first of all, we're going to split all this. So we're going to split the denominator between the two different numerators, and that doesn't change anything. That's going to help us work on it even better. Now next, you can actually again put these numbers in brackets, and then we can factorize out the power x. So that's what happens. So now 2 over 7 are both to the power x, and 3 over 7, 3 and 7 are actually both to the power x. So next we can actually see that when we integrate them, you remember that ln of a shall be equal to ln of remember that when we're told to integrate an a power x, as we've just stated recently, remember that a power x shall be equal to ax over ln of a. So that's the same rule that actually applies here. So when we say we're integrating 2 over 7 to the power x, now we have 2 over 7x over ln 2 over 7, and that's what we actually have there. And it's the same thing for this. This is what we end up having. But of course, don't forget that we have limits, because this is actually a definite integral. Now if we work on this further, we can actually insert in the limits where there is x, and this is what we end up having. So we have the group where we have x being equal to 1, and then the group where we have x being equal to 0, and then we find the difference between the two. Now anything to the power 0 is 1, so that's why we have 1 1, and then here anything to the power 1 is actually that item itself. So when you simplify further, we can actually open brackets. When you open brackets, this negative sign is affected, and that's why we have it happening like that. And then if we solve further, we can actually clearly see that we can actually group different items that actually have the same denominator, because that will allow us to solve the fractions quicker. So group those that have the denominator ln 2 over 7, and those that have the denominator 3 over 7. And then once I do that, we can actually see this group minus this is going to be negative 5 over 7 over ln 2 over 7, plus then this group divide by, so this group subtracting them, so this divide by this is going to be negative 4 over 7 over ln 3 over 7. And then our answer shall be negative 5 over, because now you can actually see that this 7 can actually be taken down, and then this 7 can also be taken down. So we have negative 5 over 7 over ln 2 over 7 plus negative 4 over 7 ln 3 over 7, and this is what I end up having as my final answer. Alright, so next, the next question, this is question number 5. I'm being told to evaluate the integral of 5 to the power x times the root of 1 plus 5 to the power x dx. Now, this is an example that also requires u-substitution. So now we basically look for the more complex part of it, and we can see that that is the value that has the root of 1 plus 5x. So the value inside, we're going to let that be equal to u. And then we can actually see that du dx shall be equal to 5 to the power x ln 5. And then if we make dx subject, dx shall be equal to du over 5x ln 5. Then therefore, it means when we substitute everything back, I'll have 5 to the power x into root of u times du over 5x ln 5. So you can clearly see that we made the right choice, because this 5 to the power x and this 5 to the power x shall cancel, and then we'll no longer have any x values left. So we'll end up just having integral of root of u over ln 5 du. Now we can pull out 1 over ln 5, because that is actually a constant, into the integral of root of u du. Now root of u is the same as u to the power a half, so when we integrate that, we'll have 2 over 3 u to the power 3 over 2 plus c. But remember that u is equal to 1 plus 5 to the power x, so therefore our final answer shall be, as you can see, we can actually multiply these in and we'll have 2 over 3 ln 5 into 1 plus 5x to the power 3 over 2 plus c, and this is the answer that we wanted. Alright, so the next question is also amazing. So this will also require us to use u-substitution. Now, as I can already clearly see, that this will actually work clearly with u-substitution. And why is that? Look at this value here at the top. Let's focus on this power. As you can see that when I actually differentiate 4y squared minus y, it is actually going to be equal to 8y minus 1. So that means basically here, it's going to bring us a value that will easily cancel out with this 8y minus 1. So that means we can actually use u-substitution. So we're going to let u to be equal to that power, 4y squared minus y. So du dy shall be equal to 8y minus 1, as you can already see. So let's make dy the subject and shall be equal to du over 8y minus 1. So therefore, our integral will be 3 into 8y minus 1 e to the power u times du over 8 minus 1. So as you can see, this and this will clearly cancel and we'll be left with the integral of 3eu du. And as you can see, we can actually pull out the 3 and we'll be left with the integral of eu du, of which that is basically going to be eu. So we'll have 3eu plus c. But remember that u is 4y squared minus y, of which our answer shall now be 3e to the power 4y squared minus y plus c. And that is our final answer. Alright, so moving on to question number 7. So we're being told to evaluate the integral of 2x cubed plus 1 over x to the power 4 plus 2x dx. Now, it seems this will also work very well with u-substitution, because as I can already see, if I look at the denominator value, I have x to the power 4 plus 2x. Now we know that when you differentiate this denominator value, I'll get 4x cubed plus 2. Now this may not exactly look similar yet, but look at something interesting. I can actually factorize out a 2 from here, and I'll have 2 into 2x cubed plus 1. So now basically later on I can see that this will actually easily cancel with that. So now I can already see what part of u-substitution I can use. So I should let u to be the denominator. So du dx is going to be equal to 4x cubed plus 2, of which I can factorize out the 2 and I have 2 into 2x cubed plus 1. So that value will easily cancel with that numerator. So if I make dx subject, dx shall be equal to du over 2 into 2x cubed plus 1. So put that into the integral and this is what I have now. So these are two values multiplying themselves. I can see that this and this will cancel and then clearly will no longer have any x value. So now I have a half into integral of 1 over u du, but we know that the integral of 1 over u is definitely ln u. So now I have a half ln u plus c. So therefore, we also remember that u was actually equal to x power 4 plus 2x. So therefore, we'll have a half ln x power 4 plus 2x plus c. And then therefore, we can actually see that this a half can actually be made a power of this from our knowledge of properties of natural logarithms. So it can be made a power of which this is the same as ln root of x power 4 plus 2x plus c, and that is our final answer. So question number 8, we're being told to evaluate the integral of ex plus e to the power x. So the powers are x plus e to the power x dx. So this will actually also require u-substitution. So now, what are we going to do in this case? So this is what we have. So what we're going to do is we're going to first separate this into two different individual values, because now this will still be complex to solve. But remember that from the properties of so remember from indices that when two values have the same powers, we actually add those powers. So basically that means we actually have ex multiplying e to the power ex. So it means they're multiplying each other and we actually added their powers. So this is basically similar. So this is where it should have come from. So what we're going to do is, now that we have something in common, we're now going to let u to actually be representing this e to the power x. So du dx shall be equal to ex, of which dx is equal to du over ex. So now basically this is what we end up having right there. So now we've let this value here to be equal to u, because we can actually see that this will actually give us a value that will easily cancel out with that value. and clearly dx shall be equal to d over ex. Now we can actually see that this and this shall cancel, and therefore we'll be left with the integral of eu du. Then therefore the integral of eu is basically clear, it's just going to be eu plus c. But remember that u is ex, so basically our answer is e to the power ex plus c, and that's the answer we're looking for. Alright, so question number 9, we're being told to evaluate the integral of 1 over x ln x dx. Now you can also see that this number here will actually work with u-substitution. And how will that be? Because we can actually see that if we let u to be equal to ln of x, and if we differentiate that, there will be a part where we'll actually get 1 over x somewhere, and you can see that that will actually allow us to cancel out that x. But let's see how that will work. So we're going to let u to be equal to that ln x, and then therefore du dx is actually 1 over x. So if we make dx subject, dx shall be equal to x du. I think you get where we're going. So if we put that back in, we have 1 over xu times x du. Now you can see that this and this will cancel, and we'll be left with the integral of 1 over u du. So that actually means that we actually made a good choice, because all x values have been eliminated. So therefore we'll have ln u plus c. But remember that u is ln x, so therefore we have ln of x plus c as our final answer. So question number 10, we're being told to evaluate the integral of e2x over 1 plus e2x dx. Now this is also an easy one. We can already see that we just have to let u to actually be equal to 1 plus e2x. So we just let u to be equal to this denominator value, because we know that when we differentiate that, basically this one will go and we just be left with 2e2x, which will actually just cancel out with the numerator. So now we can say that dx shall be equal to du over 2e2x. Now when you put that back, this is what we have. You can say that this and this will cancel, and definitely all x values will go, and then we'll be left with this. So you can pull out a half, so we'll be having a half into 1 over u du. But remember that integral of 1 over u is actually ln of u, so we have half ln of u plus c. But remember that u is actually 1 plus e2x, as we've actually said right there. So we put that back, and we have a half ln 1 plus e2x plus c, and that is our final answer. Question number 11, we're being told to evaluate the integral of e to the power 2x over 1 plus e power 4x. Now, as you can already see here, now we don't need to rush directly to actually substituting this as u, because you can already see something amazing here. You know that e power 4x is actually the same as e power 2x, let's say, all to the power 2. So it's like squaring this value right here. So when you square this, we actually get e power 4x. So you can actually say there is something in similar. So now we can actually see that this is actually how it can also be expressed. So what we're going to do is we're going to let the u to actually just be equal to this e to the power 2x. So when you do that, we can say that du dx shall be equal to 2e2x, of which dx, when we make it the subject, it shall be equal to du over 2e2x. And then therefore when you substitute that, you can actually see that this and this will cancel, and then I can pull out a half. So I'll have a half into the integral of 1 over 1 plus u squared. So now we need to remember something. So remember that from derivatives that we covered earlier, that if we had a value of if we're told to differentiate tan inverse of x, remember that we were told that the answer shall be equal to 1 over 1 plus x squared. So that means basically if we're told to integrate this side right here, it will take us back to tan inverse of x. So in a similar way, if we're trying to integrate 1 over 1 plus u squared, so you can clearly see that this will actually give us tan inverse of u. So we now have a half tan inverse of u plus c. But remember that u is equal to 2x, e2x. So basically when you substitute that back, we have a half tan inverse of e to the power 2x plus c as our final answer. So question number 12, we're being told to find, now this is an example that actually is a definite integral. So we have the upper limit as e squared, and then the lower limit as e, into 1 over x, then ln of x. So this is actually squared. Now I can already see what I'm going to let my value of u be, because this is going to clearly you need u substitution. So I'm going to let u to be equal to ln x. So when I do that, du dx shall be equal to 1 over x, and then when I make dx subject, dx shall be equal to x du. So therefore when I put that back, I can see that this will easily cancel and eliminate this x value right there. So I have the integral into 1 over x u squared times x du. So this and this will cancel, and I'll be left with the integral of this. So I'll only be left with 1 over u squared du. But remember that this can be expressed as u to the power negative 2. So when I actually integrate that, I have u to the power negative 1 over negative 1. So now basically, because of this negative 1, you can see that this will become negative u to the power negative 1 with the limits outside, as you can see. But remember that u is actually ln x, so basically we'll have negative into bracket ln x to the power negative 1, and then e with the limits outside. So next we're going to actually plug in the limits. So when I plug in the limits, this is what I'll end up having. But remember that ln of e to the power 2 is actually basically, so it means from that knowledge of natural logarithms that the ln of e we're actually just going to remain with the power. So the ln of e right here we're just going to remain with 2, and then ln of e alone is actually 1. So now basically we have, so 2 to the power negative 1 is basically a half, so we have negative a half, and then this 1 to the power negative 1 is basically 1 over 1, which is actually that, so which is actually 1, so we have negative 1. So in that negative times this, so actually we get this negative 1 right, 1 over 1 right here. But now this negative and this affect each other, and we'll have a plus. So we have a negative a half plus 1, which is basically equal to positive a half, and that is going to be our final answer. So now that we've done those, there is an exercise I have for you. I encourage you to try this out and then compare your answers to the answers you can actually see on the right hand side of each question. And I believe that after you've done these questions, you'll actually have a better understanding of integrals of exponentials and natural logarithms. Thank you so much for watching. I'll see you in the next video. Thank you so much for watching this video. I hope the video really helped you. If you did, feel free to tell me below in the comments. I'll make sure to get time to read through your comments and to reply to you. And also, if you're new to this channel, I encourage you to join the community by subscribing, and then make sure to hit the notification bell so that you get updated every single time I upload a new video. Again, my name is Emmanuel Olega. Thank you so much for watching. See you in my next video.